Welcome back. In deriving the maximum likelihood and map estimates of the original image, we need to stochastically model the original image and the additive noise by defining their probability density functions. These represent our prior knowledge about the original image and the noise, and they're therefore justifiably referred to as prior models. Then, based on Bayes' theorem, our prior knowledge is modified by the likelihood function. It represents the most probable image that gave rise to the observed data, to form the probability of the original image after the degraded image was observed, justifiably referred to as the posterior density function. If the likelihood function is maximized, in other words, no image prior model is used, a maximum likelihood estimate of the original image results. If, on the other hand, the posterior is maximized, then a map estimation results. We derive the exact expressions for the maximum likelihood and map estimates for a Gaussian noise model and the so-called simultaneous autoregressive image prior. We see that familiar expressions result in this case, that is, the expressions for the least squares and the constrained least squares, or Wiener filters. So let us now look into the fine details of this material. Let us now discuss the Bayesian formulation of the image restoration problem. We will derive the maximum likelihood and map estimates under specific prior models, and we will say a few words about the hierarchical Bayesian approach. We show here in matrix vector form the gradation model we have been using all along. So Y is the observed image, H the known blurring matrix, F the original image, and W the additive noise. With stochastic approaches, F is assumed to be a sample of a random field, and so is W, and therefore Y becomes a sample of a random field. From here clearly I can write that W equals Y minus HF. So the standard model that has been used to model noise is the normal or Gaussian distribution, named after Gauss. This is the celebrated distribution that has found numerous applications from image processing we're discussing here to economics and beyond. So this is the expression for the multivariate Gaussian distribution. So this is the probability density function of Y given F. CWW is the covariance matrix. And these vertical bars denote the determinant of the matrix. We assume that the image has n samples. We can further simplify this model if we assume that in addition to being Gaussian, the noise is also white. This means that the covariance matrix is equal to a constant times the identity matrix. Therefore, its determinant is equal to beta to the minus n, since again the image has capital N pixels. And from here, of course, the inverse of this is just beta identity. So the form this distribution takes is shown here. This symbol denotes that the left-hand side, the probability density function of Y given F, is proportional to the expression on the right. And clearly here I have the inner product, Y minus HF transpose times Y minus HF, which gives rise to the norm squared. So this is the standard model that has been used almost exclusively, I would say, for this additive type of noise in all stochastic approaches, and we're going to proceed with this and see how it affects the calculations we are going to undertake. As we discussed earlier when we were talking about deterministic restoration techniques, prior knowledge is of the utmost importance in solving restoration recovery type of problems. since they restrict the solution space. So with the deterministic approaches, we assume that the original image is smooth, and the way you did that, we constrained the energy of the image at high frequencies. So we took a Laplacian, a high-pass filter, and filtered the image. We measured the energy at high frequencies, and we tried to make that quantity as small as possible. We can do a similar thing here by imposing this simultaneous autoregressive, as is typically referred, SAR image prior. So the original image, this is the probability density function of the original image, is proportional to a Gaussian here, an exponential, with this in the exponent. If we expand the norm, then I have this expression here. So this is a zero mean Gaussian with inverse covariance here equal to alpha C transpose C. So C again is a high-pass filter here, such as a Laplacian, and one way to interpret this prior knowledge is if we look at this again at the norm, when the energy at high frequencies is small, then I have e to the minus a small number, so that's close to 1. So images that are smooth, images that have low high frequency energy are more probable according to this model. We'll look at other image prior models later on, but let's proceed with this and see how we can find a restored image based on these two models, for the noise in the previous slide and for the image in this slide. We show here the joint distribution between f and y. So it's the probability of f and y, and according to the product rule of probability equals the conditional of y given f times the marginal distribution of f, or the probability of f. Similarly, the joint between y and f is shown here according to this product rule. Now, since these joints are equal, the right-hand sides are equal as well, and this gives rise to Bayes' theorem. So this expression is the expression of Bayes' theorem. So this is the posterior, the probability of the unknown image based on the data. So equals our prior belief or knowledge about the image. And this is the likelihood function. So our prior is altered by the likelihood to give the posterior. And the likelihood is the most probable f here, original image, that gave rise to the data. So according to the maximum likelihood estimation approach, we find an estimate of the original image which maximizes this likelihood function. We find again the most probable original image that describes the data we observed. We also have the maximum a posteriori, or map estimate, which maximizes the posterior, since the denominator here, denominator of the posterior is independent of f, it's not included in the optimization, so it's the argument which will maximize the likelihood times the prior. So both are some of the commonly used estimation approaches, the maximum likelihood and maximum a posteriori. And we'll see next, under the models we introduced earlier, what are the estimates we obtain under these two conditions. Let us see now what is the expression for the maximum likelihood restored image for the Gaussian noise model that we introduced earlier. It's shown here again, so this is the condition of y given f. I only keep the terms that are relevant to the optimization, and therefore I use here the proportionality symbol. CWW minus 1 is the inverse covariance matrix of the noise, so I do not use the assumption yet that the noise is white. So according to the maximum likelihood estimation approach, we need to maximize this conditional probability here. Since there are exponentials involved in these Gaussian functions, a standard trick, if you wish, we do, instead of maximizing the likelihood directly, we maximize instead the log of the likelihood. Since the log is a monotonically increasing function, the maximum point does not change due to that. So I maximize the log of the likelihood, and if we take the log of the exponential, then the exponent just comes down, and therefore I need to maximize this expression. Now maximizing a negative function equals to the minimization of the positive function, and therefore we need to minimize this norm. So I've taken the inverse covariance and I've just used it here as the weight of this norm, so I have to minimize this weighted norm. We looked earlier of what is the minimum of a weighted norm, and if you follow the steps that we just explained earlier and used it actually multiple times in these 2 weeks that we cover restoration, we can easily find that the maximum likelihood estimate is given by this expression. So this is the generalized inverse here, in case the matrix is not invertible. Now if the noise is white, then the covariance equals to beta minus 1 identity, so this is actually the variance of the noise. And in this case, if I substitute CWW in the expression above, I find that the maximum likelihood estimate is given by this expression. So this is exactly the expression we obtained when we covered least squares restoration in the deterministic fashion. This result holds for any matrix H. If the degradation is due to the linear spatially invariant system, then we know that H becomes block circular, and furthermore we can take this expression to the discrete frequency domain, and this is what we call the generalized inverse or the inverse filter. So we see that under the assumption of Gaussian noise, the result of the maximum likelihood restoration equals the result of the least squares estimation in a deterministic fashion, and here is a weighted least squares, and here is the unweighted least squares, or the inverse filter that we developed early on when we started talking about restoration. Let us look at the expression we can obtain for the map-based restoration. We will use the noise model that we introduced earlier and used also for maximum likelihood, and for the image prior we'll use this SAR model that we also introduced earlier. I'm reminding you here that the inverse covariance of the image, it's simply equal to alpha C transpose C, something you can see right away if you expand this squared norm here. According to the map estimation formula, we're looking for F here, the restored image, that will maximize the log of the posterior. This is the numerator of the posterior, the denominator is independent of F, so I have the likelihood here and the prior. So if we multiply the exponentials and take the log, the exponents come down, and also instead of maximization as before, I carry out a minimization of the negative function. I've used the noise covariance here as a weight to this norm. So we have this sum of a weighted norm and the L2 norm. Again, we've looked at this multiple times and in different versions. We know that we have to take the gradient of what's inside the brackets and set it equal to 0, and if we do so using what we have learned and used multiple times in this class, we can obtain that the map estimate is given by this expression. So this is again the generalized inverse, this plus, and we see that both the, as expected, the noise covariance is involved and this parameter alpha. Now, if the noise is white, then this is the noise variance here, and if I substitute this expression in what I already obtained, we find this form for the map estimate. So you see right away, this is the familiar constraint least square solution that we obtained when we talked about deterministic restoration. Instead of a ratio alpha over beta here, we had one parameter, let's call it lambda, the regularization parameter or the Lagrange multiplier. We also know that the CLS filter is equivalent to the Wiener filter based on the appropriate interpretation of the error covariance and the image covariance. And more specifically, if I substitute here for the image covariance this expression, then from here this is the same expression I obtained from the Wiener filter. So in summary, under these two specific models for the noise and the image, our prior knowledge about the image, we see that the map restoration gives exactly the same result as the constraint least squares restoration and the Wiener restoration that we have covered before.